Welcome and thank you for attending this session at Parma Data Saturday. My name is Dennis Torres. I'll be talking about SQL Server 2022 Intelligence Query Processing, new features. So, thank you for the sponsors of this great conference. Without their help, this conference would not be happening. And this is me. I'm a data platform MVP. I have some Microsoft certifications and I live in Malta. I'm the leader of the Malta Data Platform User Group. You can see on the screen my contacts. It will be a pleasure to stay in touch. Connect on LinkedIn, Twitter, YouTube, and you can send me any questions about this session or other questions you may have. It will be a pleasure to stay in touch. Our agenda today. First, we need to understand the past to understand the new query processing features. These query processing features are evolving since many past SQL Server versions. So we need to first to understand the past. We will talk about query store hints, parameter sensitive plan optimization, DOP feedback and C feedback. So, you have to know the past to understand the present. A message from Carl Sagan. And that's what's happening with SQL Server. The query processing features evolved a lot, especially since SQL Server 2016. They started to evolve over previous evolutions, and now to understand what we have, we need to fully understand the past features to understand the present features. So let's talk about them. Before 2016, before SQL Server 2016, what we had? We had the query plan cache. SQL Server had the query plan cache. The executed queries would have their plan in the query plan cache while they are still, let's say, in use. If someone comes to us and says something like, oh, my queries sometimes are slow, sometimes they are faster, or my queries are becoming slower and slower. We only have the query plan cache to check this information, and usually that's not good enough. So only the current queries in the cache. A restart of the SQL Server, if we restart the set, it clears the cache. No history. We have no history about what query plans the queries are using. What are the query plans the queries are using? We had no history about that. Then we had SQL Server 2016. In SQL Server 2016, we got Query Store. Query Store is enabled on the database level and keeps a history of the query plan that each query is using. This happens besides the query plan cache. So even after a restart, even if we are not using, a query is not using that plan in the query plan cache anymore, the history is inside Query Store. So queries and plan history are stored inside Query Store. And this allows us to identify what's called a query plan regression. In fact, this name started to be used in 2016. What's a query plan regression? Is when a query is recompiled and the new plan for that query is worse than the previous plan for that query. This is called a query plan regression, And without the history that we get inside query store, we can identify this. We can identify the query plan regressions. And creating a baseline for how our server behaves became very easy. It's very easy to create a baseline because the query store also stores some information about the execution of the queries, some statistics about the execution of the queries, so we can identify a baseline for our query executions, using query store to create a baseline for our server. And we can identify a very difficult problem called parameter sniffing. We can identify, but at this point query store is not providing a solution for it, but it's providing a way to identify queries causing this problem, the problem called parameter sniffing. We'll talk more about this. Then it came the SQL Server 2017. SQL Server 2017 brought a set of new features called adaptive query processing. This was a very important evolution in the line of evolution of query processing features. Why? Because these features under adaptive query processing, they are capable to change a query plan inside the query plan cache after the query plan is already compiled. So after the query plan is already compiled, the plan can be changed if SQL Server identifies that a change is needed. So this feature, adaptive query processing, broken down in 3 different sub-features, let's say like this: memory grant feedback, adaptive join, and interleaved execution. This completely changed the way we look to the query plan cache, because before that the query plan cache was completely static. Then after 2017, the query plan cache can be changed if SQL Server decides that it's useful to change, to improve one specific query. So the cache is not immutable anymore after 2017. The first feedback was created. What do I mean about feedback? The one in this case is the memory grant feedback. It's a set of query processing features called feedback. Is when SQL Server is analyzing the execution of our queries and trying to identify what could make our queries better. Each feedback feature is analyzing one point of view in relation to our queries. And the first feedback which was created was in 2017. It was the memory grant feedback. It was capable to analyze the memory grant for our queries and adjust the memory grant for our query. A query could be extremely slow if it's executed with a bad memory grant. It could cause a spill of the data to TempDB, for example. And by using this feedback, we could avoid this problem. Parameter sniffing has partial solutions. Here again, we are talking about parameter sniffing, and I'm mentioning that we have a partial solution for this problem. Why? What do I mean about a partial solution for this problem? I mean that a parameter sniffing problem could cause a bad memory grant. So the memory grant feedback could solve this problem. And a parameter sniffing problem could also cause a bad choice of joins inside the query plan, and we had the adaptive join to solve this problem. So we had some features, some query processing features that were partially solving the parameter sniffing problem, far from completely, but partially helping to solve and reduce the parameter sniffing problem. We'll get back to this and talk more about parameter sniffing. But the features in 2017, the features created in 2017 were very focused in batch mode. In fact, this difference between batch mode and row mode existed since SQL Server 2012. But this was the first time some features were focused to work only in batch mode and not in row mode. Let's talk a bit more about what is this. And to complete the set of new features in 2017, we had the plan forcing recommendations. What this means? Since it was created, Query Store allows us to force another plan to solve the query plan regression that we were talking about. We can force another plan. If the newer plan is not good enough, we can force another plan. Of course, this is not a perfect solution. There are many problems about forcing one query plan, one specific query plan, but it's possible. It's possible to force another query plan. On 2017, the same Query Store started to give recommendations about which plan we should force and when we should force a plan. So we started to get recommendations from the Query Store. Query Store was telling us what to do, what we should do. And we could use these recommendations and analyze these recommendations. But let's talk about this batch mode that I mentioned. What I'm talking about? I'm talking about the query processing and the storage of the data. Query processing and storage of the data. The processing can happen in batch mode when the data is stored in a format called column store. What this means? This means exactly the column store indexes. When our table have column store indexes, the processing of the query will happen in batch mode. This means the records will be retrieved and processed in batches, which makes the query faster, usually faster, and good for analytical processing, although it's bad for production processing, because usually in production we need to access individual records and not exactly the records in batch. So this is a good processing for analytical processing. The other processing mode was older, way older. It is called row mode, processing in row mode, and it happens when we use row store. What's row store? This is our usual clustered and non-clustered indexes, or even a heap. This is what we call row store and row mode processing. And the point is, the features created in SQL Server 2017 were focused on batch mode. This feature only worked in batch mode when our tables had a column store indexes. In raw mode, these features were not available. So this was a limitation in SQL Server 2017. Then it came SQL Server 2019. Well, things evolved so much, they had to create a new fancy name for this set of features, and it became Intelligent Query Processing. It was not possible anymore to put the features under the Adaptive Query Processing name because they were not related. So they created the fancy new name Intelligent Query Processing. And batch mode is not a limitation anymore. How this happens? Well, first, memory grant feedback over raw mode was available in 2019. In SQL Server 2019, we got the memory grant feedback over raw mode. That was great. And we got batch mode execution, batch mode processing over raw store in tables without a column store index. The batch mode processing could happen in tables without a column store index. And since batch mode was happening, the features which were exclusive from batch mode, like adaptive join, could take place as well. So batch mode was not a limitation anymore in 2019, in SQL Server 2019. Then we got SQL Server 2022. What is new in query processing in SQL Server 2022? Query store is enabled by default. Since SQL Server 2016, Query Store was disabled by default, and Query Store can be enabled or disabled on a database level. We can enable or disable on a database level, but Query Store is collecting and saving data inside the database. So there was always a concern about the overhead that this could cause. The point is that on most of the times the benefits are higher than the overhead, than the problems of the overhead. And the problems of the overhead can be worked around with a good query store configuration. So in SQL Server 2022, Query Store is enabled by default. Then we got Query Store Hints. This is an incredible feature, a great feature. What are Query Store query hints? Well, you know query hints. You can put a query hint in a query to make a turning of a query and improve the performance of that query. But now you could do so through Query Store. We'll talk more in some moments. Feedbacks are persisted. We talked just a minute ago about the memory grant feedback. But the memory grant feedback was an information stored in the query plan cache. It was changing the query plan in the query plan cache. If we restart the server, we lose the feedback. But now the feedbacks are persisted inside Query Store. Inside Query Store, the feedbacks are persisted. So we restart the server, the query plan cache is cleared, but that feedback for that query plan is stored in Query Store. This means that the entire compilation and execution process of a query has changed. Because when a query arrives in SQL Server and the query will be compiled, SQL Server 2022 will check Query Store for the existence of some feedback in relation to that query, some feedback in relation about how the compilation should be made. So the compilation process and the execution process changed in relation to this flow. What I was saying, the query processor workflow changed. Feedbacks are all around. We don't have anymore only the memory grant feedback. We have a lot of feedbacks for our queries. Parameter sniffing is finally solved. Some people would say that, oh, it could still happen. Yes, it could still happen. But now we are reducing parameter sniffing to a minimum, thank you to a new feature in 2022. So let's start talking about query store hints. To start this set of new features, let's start talking about query store hints. What are query store hints? The idea is that we can apply a hint in a query inside query store. Why is this important? Well, we use hints to improve the performance of a query. If the plan generated for a query is not so good as we would like, we put a hint on the query. But who is executing that query? You may have an application executing that query. In your company, there may be an application executing that. So, if you decide that that query needs a hint, you need to send that query back to the developer. The developer needs to implement that hint in his code, in the source code of the source application. This would be very difficult. That's why the query store hints are a great evolution, because we can apply hints to query plans inside query store. This means that we can change the behavior of the query plans using query hints without changing anything in the source application, without changing anything in the source code, only by using query store. So we can adjust query performance with no code change. The hint is persisted inside query store. It's not something that is only inside the query plan cache. So if the server restarts, the hint is still there, persisted inside query store. Query processor honor the hint. What this means? The server restarts, the query arrives again, the query will be compiled again, but the query processor checks query store and discovers there is a hint for that query. So the compilation happens with that hint. And we can use query store data to follow up the results. I mentioned before how query store is great to make a baseline. We can also use to investigate the results of our optimizations. We can apply a query store hint and check the data in query store to be sure that the performance of that query improved after we applied the query store hint. Let's see a demonstration about the usage of query store hints. So I have some databases here. I have 2 AdventureWorks and 2 worldwide importers. I use each database for a different demonstration. For the query store hints, I use the AdventureWorks 2019. So I'll be creating a store procedure. Let me clean the environment and create a store procedure called filter price. I'll be filtering the table called big product by the list price field of this table. This table, big products, is not built in on the Adventure Works 2019 or any Adventure Works. There is a script called make big adventure, which creates this table. Creates in fact two tables. Create a table big product and big transaction history. So if you want to reproduce this example at your home, you will need this script. You need this script make big adventure to create these tables. Now I'll create an index over the list price. Some of you may be noticing this is not something usual. Filter a product by the list price, the values that are equal to the list price. Yes, it's true. It's not usual at all. It's not something usual, a usual business case. But I'm using this exactly to create a very common problem that we face. What's the common problem that we face? Parameter sniffing. What is, after all, the parameter sniffing problem, which I'm talking since the beginning of this session? What is this problem? What is parameter sniffing problem? So, parameter sniffing problem happens when the data is skewed according to the field that we are looking for. In this case, the field is the list price. So I'm using this query here, grouping by list price, making a count to see how many records, how many products we have with each different price value. So, on the highest amount, we have the value 0. There are 10,000 products which cost 0. So, if I make a query looking for a product costing 0, the query will return 10,000 products. On the other extreme, we have a set of many different product prices, list prices, that return only 50 records. This is what we call skewed data. This means that sometimes the query will return 10,000 records. Sometimes the query will return 50 records. Of course, the best query plan to return 10,000 records may not be the same as the best query plan to return 50 records. They should be different plans. They should be different. So let's make an experiment. I'll execute the stop procedure first with the value 121.49 and then with the value 0. The point is, executing the procedure this way, I'm using the with recompile. This means that for each execution it will you recompile the procedure and use the best plan possible. So let's see the actual execution plan. I'm including here the actual execution plan and execute. So for the 121.49, there were 50 rows as a result, and since there were only 50 rows as a result, the best plan was to use an index seek and a key lookup, because the number of rows is not too high. It was okay to use even a key lookup because the number of rows was not too high. But if I execute the procedure with the parameter 0, I have 10,000 rows as a result. And the best plan in this situation is to use a cluster index scan. Because in this case, that other plan would be terrible for this query. So the best plan for the value 0 is a cluster index scan. See, this is what we call parameter sniffing problem. It's the same code, the same stop procedure. The only thing changing is the parameter, and the parameter causes a difference in the query plan. For one parameter value, the plan should be 1. For another parameter value, the plan should be other. So it's causing a difference on the plan. So now I'll clear the procedure cache. Start with a clean procedure cache. Let's see what happens when I execute these procedures without using the Whisper compiler. Let me execute first with 12149. Execute. It returns 50 and it uses the index seeking key lookup. Now let's execute the second one with the parameter 0 and let's see what happens. So the second one returns 10,000. Let's check the execution plan, and it's also using an index seeking key lookup. I used a small amount of data, so we would not leave this running forever. But this plan is terrible for the performance of this second stop procedure. But why it was used? Because it's based on the parameter used on the first procedure. The procedure was compiled here because the plan cache, the procedure cache was clean. So the procedure was compiled based on the first plan. On the second one, it is using the compiled plan. It doesn't matter the parameter. It's using the compiled plan. Even if the compiled plan is terrible for that parameter value, but it's using the compiled plan. This is the problem that we call parameter sniffing. So we call this problem parameter sniffing. We can take a look on Query Store inside AdventWorks 2019 and check the top resource consuming queries. And we can see the top resource consuming query here is the query making a select from big product where list price equal the parameter. And it's using this plan, the plan 25. And how do we identify there is a parameter sniffing problem? See the difference? There were the plan 26, and the plan 26 appeared to be way better for a different parameter. But here, in fact, I haven't executed enough times to have an information about that. The point is that we would see the same plan executing sometimes very well, sometimes in a terrible way. That's how we would identify a parameter sniffing problem. The same plan, the 25, when executing for the value 12149, it will be great. When executing for the value 0, it will be terrible. So we will see the same plan varying a lot in performance. That's how we identify a parameter sniffing problem. And how do we solve the parameter sniffing problem? Well, there are many solutions here, but my purpose here is to illustrate how we can apply a query store hint. And we saw that if we recompile the query, the procedure of the specific query, if we set that query to be always recompiled, the query will be always using the best plan possible for the parameter value. So let's find the query that we have. Let me check the query ID, top resource consumption. The query ID is 808. 808, I'm sorry, these are old queries in Query Store. The correct one is the 808. So I use the 808 and apply the option recompile query hint to this query. I will make this application of the query hint by using the procedure sp query store set hint. Set the hint for this query. That's it. I can check the applied hint by querying the sys query store query hints. By making this query, I can see that there is a hint applied. Option recompile for the query 808. So I have a hint applied for this query. I'm sorry that before the demonstration I failed to clear the query store. I should have cleared the query store from previous demonstrations. But what's important is that the query 808 now will be using this hint option recompile. We can clear the cache just to be sure about what will happen. We can clear the cache. Here it is, clearing the cache, and now I will execute the procedure with 1-to-149. Mind that I'm not using with recompile, and the query plan used is the key lookup. Now I will execute the same procedure with the parameter 0. I will execute, and it's using the clustered index scan. I'm not executing them with the with recompile, using the with recompile, but the option recompile is being applied to the query that this procedure is used. The query is using the option recompile, so each procedure is using the best plan possible for that query, and that's absolutely great. And I did this without changing the source code. I never changed the filter price procedure. I never changed the source application. I just apply through query store a hint to one query. I identify the query and apply a hint to that query using query store. That's it. This is the power of the query store hint. If for some reason you feel that, oh, but I heard about this before, this is not really something new. You heard about this before because Microsoft is using a practice to, they call this practice cloud first. They implement some features in the cloud first, and then they implement on-premise. This means that this feature was already released in Azure SQL Database about 6 months ago. Azure SQL Database are able to use query hints for 6 months already, but only now in SQL Server 2022 we are able to use query store hints on-premise or in SQL Server inside virtual machines. Only now this is available for on-premise or virtual machines environment. Let's get back to our slides. Now let's move to another subject. Let's talk about DOP feedback. What's DOP feedback? DOP is degree of parallelism. We have a server level configuration called max degree of parallelism, or MaxDOP. We can configure this on server level. Some versions ago, SQL Server enabled this configuration on the database level. We can have a MaxDOP configuration on the database level. But how many servers did you find with a bad MaxDOP configuration? Either on the server level or on the database level. How many servers you already found with a terrible MaxDOP configuration? A lot? That's it. So, SQL Server 2022 now have a DOP feedback. It means that when a query goes parallel, SQL Server 2022 will analyze if that execution is really good for the query. If SQL Server believes that query should not be using that degree of parallelism, that degree of parallelism is not good enough for that query, SQL Server will try to reduce the degree of parallelism. If the query is using too much parallelism, it will only create problems to the query. It's like the old saying, a project that should be completed in 12 months by one developer will not be completed in 1 month by 12 developers. It will not be this way. So sometimes we see our queries using too much threads to be executed, and this will make the queries slower. So SQL Server will analyze that and automatically reduce the MaxDOP of the query by using the DOP feedback. So, DOP feedback. Identify parallelism inefficiencies. What are parallelism inefficiencies? For example, wait, too many wait, CX packets, and other weights related to parallel execution. If SQL Server identifies that one query is not efficient by executing in parallel with the current MaxDOP configuration, it will try to put the MaxDOP down. Not the MaxDOP in general, but for that query. Inefficiency based on CPU time, elapsed time, and wait. It will lower the MaxDOP for that query. We'll make evaluation cycles until stabilize the query. A basic rule that the Microsoft developers followed when creating this kind of feedback was to don't harm our environment. So, When they decide to lower the max DOP, they create evaluation cycles to be sure that the result of lowering the max DOP really improved the query. If they decide during an evaluation cycle that the result didn't improve the query, they cancel it. They don't lower the max DOP, they cancel this process. And they follow this until they stabilize the query. They reach a point where they can't lower anymore the max DOP. They can't put down anymore the max DOP, or the query is already good enough. If they lower more, the query will get worse. The ceiling is always the max DOP or the max DOP hint. It means that it will never disrespect our configurations. And the intention is to put down, not to put up. It will only put up if after putting down, it discovers, oh, something changed. This query is not efficient anymore. Let's go back up to the max DOP configuration to see what's the best level for this query. So, it depends on query store history. That's extremely interesting. To make the DOP feedback work, SQL Server uses the query store history. Query store is collecting execution history about the queries. And SQL 2022 use this history collected by query store to identify if the query needs a DOP feedback or not. And the feedbacks are stored, are persisted inside query store in a DMV called sysquery store plan feedbacks. Not only the DOP feedback, but also the memory grant feedback and other feedbacks as well. These feedbacks are persisted inside this DMV. It's revalidated when the cache is cleared. The feedback is persisted. Why the feedback is persisted? So, if the cache is cleared, the feedback is there. Okay. But SQL Server will not trust blindly on this. After the cache is cleared, the query arrives again, needing to be recompiled. The feedback is there, so what SQL Server will do? Will revalidate the feedback. We'll check if that feedback is still valid to continue stabilizing the query again. So, after clearing the cache, the feedback is applied from query store. This feature, DOP feedback, can be enabled or disabled at database level. You can decide if your database will use this feature, DOP feedback, or if your database will not use DOP feedback feature. You decide. And this feature can be monitored using extended events. We can use extended events to check what's happening. Let me show an example of what happens in relation to extended events when we are monitoring a huge workload and some queries, one query or some queries need DOP feedback inside this workload. So, in case of a new feedback, we will see the event called DOP feedback eligible query. This means that SQL Server identified there is a query that should have a DOP feedback, a DOP feedback. And then SQL Server provides the feedback, DOP feedback provided. There is a 7 minutes difference between these events. What this means? Between the moment SQL Server identified the query was eligible and the moment the feedback was provided, SQL Server was making many internal calculations to identify what would be the perfect DOP feedback for this query. And after the feedback is provided, the validation happens. Multiple validation events is checking if the query really got better, until it decides the query is stabilized. You can see the timestamp on these two last events. The last validation decided, okay, the query is stabilized. So the last validation event triggers the DOP feedback stabilized. The query is stabilized and will use the feedback. The feedback is only persisted inside query store after this stabilization, the stabilized event happens. This happens for a new feedback. But what if we clear the query plain cache and execute again? After the cache is cleared, when the query arrives in the server, the first event that happens is the DOP feedback provided. DOP feedback provided. The eligible query doesn't happen because SQL Server knows there is a feedback for this query, but SQL Server will validate the feedback. So it goes directly to feedback provided and validate the feedback of this query until it confirms, okay, the query is stabilized. The query is stabilized, the query is with the best feedback possible. So, some people would say, I will lose my job with a feature like this. Now SQL Server is doing everything for us. Everything. SQL Server is doing everything for us. We will lose our jobs. No. There is, let's say, I would call this a shift on the work of the DBA. We will shift our work to more interesting areas. For example, we need to investigate the extended events to see the feedbacks happening. If we have too many DOP feedbacks on the workloads on the server, probably this means that the max DOP configuration for the server, or at least for the database level, is not good enough, because it's generating too many DOP feedbacks. If you have too many DOP feedbacks, putting down the max DOP of each query to the minimum possible. What's the minimum possible? The minimum possible is 2 threads. The DOP feedback will never remove the parallelism and make the query execute without the parallelism. So the minimum possible value is 2 threads. And if you have too many or all your DOP feedback putting down the max DOP to 2 threads, this means that probably the cost threshold for parallelism in your server is not good enough. This means that you are getting queries that are too small and put them in parallel, because this configuration is wrong. Small queries should not be in parallel, and in this case the DOP feedback will not help you enough. Because the DOP feedback will stop in true. Maybe these queries could even be better if they were not parallel at all. But this is a DBA decision. This is a check that the DBA needs to do. Too many queries executing on the maximum value of the max DOP may mean the DOP configuration is too small. If all the queries or too many queries are executing on the maximum max DOP, the DOP may be too small for these queries. So, how can I illustrate this? Bob Ward created a great demonstration about this, but this demonstration takes a lot of time to execute, 20, 40 minutes to execute. So what I have here to illustrate are the events in extended events. Exactly the same sequence that I illustrated in the PowerPoint. Eligible query, feedback provided, the validation until the query is stabilized. This execution was generated based on a workload, on a sample workload created by Bob Ward, and is available on his GitHub. I will provide the link to his GitHub on the end of the session. Don't worry about that. So that's it. We can see the DOP feedback happening here. And we can query. We can make a select. Query store plan feedback. So if I execute this here, we can see that the workload, the sample workload generated by Bob Ward generated some memory grant feedbacks and generated a DOP feedback. And the less good feedback was 2. It really reduced the DOP of the query to the minimum. Baseline stats, the original was 4, and it reduced the less good feedback of this query, it reduced the feedback to 2. Okay. So let's continue on our PowerPoint. Now let's talk, now that we talked about DOP feedback, let's talk about parameter sensitive plan optimization. I mentioned to you that SQL Server 2022 brought a solution to parameter sniffing. We have a solution for parameter sniffing. That's it. Parameter sensitive plan optimization. It's also called PSP feature. And in a simple way, explaining in a very simple way, it allows the same query to have multiple active query plans inside the query plan cache. So the same query can have multiple plans inside the query plan cache using this feature. How this happens? So parameter sensitive plan optimization. The idea is multiple query plans for each query. We can have multiple query plans for each query, based on the query statistics. So SQL Server will analyze the query statistics and analyze the number of rows that the query is returning on each parameter value. If SQL Server identifies that this query is too skewed, this parameter is too skewed, SQL Server can use PSP to create multiple query plans for the same query based on the parameter values. It doesn't depend on query store. PSP is a new feature that doesn't depend on query store to work. We have what are called dispatcher plans and variant plans. So, one same query will have multiple plans, yes. And we will have one plan which is called dispatcher plan. The dispatcher plan is the one that will be the responsible for executing the query. And the dispatcher plan, according to the statistics and according to the expected number of rows of that query, will trigger the correct variant plan. So the dispatcher plan will decide the variant plan to be triggered. Variants are defined by the range of returning rows of the query. How many rows the query will return. So according to a range of returning rows of that query, we'll have different variant plans. So we can see here what would be an example. Parameter sensitive plan optimization. We have a parameterized query. A dispatcher plan is created. And from this dispatcher plan, 3 variants can be created. 3 variants can be created from this dispatcher plan. See, it's mentioning the number of rows, 10k. And between 10k and 1 million. These 3 variants are based on the same number of rows. 10k in one side and 1 million in another side. So each dispatcher can have a maximum of 3 variants. What this means? The first variant used for when the query returns less than the minimum number of rows calculated by SQL Server. So the first variant will be used. When the query returns the number of rows between the minimum and the maximum number of rows, the middle variant, the second variant, will be used. When the query returns a number of rows above the maximum number of rows calculated by SQL Server, then the third variant will be used. So, for one parameter, for one dispatcher plan, one parameter, we can have 3 variants based on a range of values. This range of values is calculated by SQL Server in a very, let's say, a very complex way to decide this range, the minimum and maximum value that will be used in relation of number of returned records, and then the 3 variants will be created. This is basically creating a very good solution for parameter sniffing. Imagine a parameterized query. If the value of the parameter arrives here, and this value of the parameter will return a small number of rows, it executes the first variant. If it will return a medium number of rows, it will execute the second variant. If it will return a very high number of rows, it will execute the third variant. And all this is based on the statistics. This process is checking the statistics to decide to which variant will be used to execute each query execution. Let's see a demonstration. So I use the second worldwide importers. Let me clear everything here. I'm clearing the procedure cache and I'm clearing query store as well on this second worldwide importers. Okay, then I will execute the store procedure with value 2 and execute the store procedure with value 4. This scenario, also the base example was created by Bob Ward. This scenario will reproduce a parameter sniffing problem. I can see the actual execution plan. For value 2, the actual execution plan is using a seek and key lookup, and then I will execute for value 4. It will take a bit longer to make this execution for the value 4 because it's returning way more records. So, after 2 minutes and 30 seconds of execution, we have the result of this execution. And it used a parallel execution using a sort and parallelism with a cluster index scan. So, the plan for the parameter 2 is completely different than the plan for the parameter 4. I'm not using with recompiled here. I'm not using with recompiled. It automatically created 2 different plans for the same query. Let's analyze this inside the query plan cache. We can make a query inside the exec cached plan and see the query plan and the query text and look for the dispatcher queries. We need to use a bit of XML to query the query plan cache and look for something inside the query plan. Let me increase this window. Okay, so 3 queries were returned. One of these queries has a text the create procedure. This is the dispatcher query. The dispatcher query used the original query syntax, original query text as the text. Then 2 variants were created. The 2 variant queries have a query hint. These two variants have a query hint. Option, plan per value, and query variant. It's identifying the query variant 1 or query variant 3. The values, the range are the same. 100 and this big value full of zeros here. So the range is the same because the range was calculated once by SQL Server, defining the range of returning records. What defines which variant is which is the variant ID. The query variant ID 1 is for the queries which return less than 100 records. The query variant ID 3 are for the queries which return more than the maximum value calculated. While I executed only 2 queries, and these 2 queries generated the variant 1 and the variant 3. There is still space for a variant 2, a plan which will be used for queries which return more than 100 of records but less than this big number of records. This will fit in query variant 2, which was not created yet. So we have the dispatcher and 2 variants, and this is coming from the query plan cache. We are finding this, locating this inside the query plan cache. So if I take a look on the query plan of the dispatcher plan, there it is. The query plan of the dispatcher plan. We can immediately identify this is a dispatcher plan for a PSP set of plans because it uses the new operator called multiple plan. So we can identify the dispatcher plan by this operator using multiple plan. While the other 2 plans are specific plans according the number of records predicted for this variant. The query variant 3 is using a parallel execution, is for the parameters which return more than the maximum number of records calculated, and the other is using a simple index sequence key lookup for the queries that return less than the minimum number of records, 100, less than 100 records. So we are seeing how it works for the query variant 1 and 3. And this information is also located inside Query Store. PSP doesn't depend on Query Store to work. Query Store could be disabled, but I can also find information about PSP query plans inside Query Store. There is a special Query Store DMV called Sys Query Store Query Variant. This special DMV shows which queries are variants. It's showing that query ID 2 and query ID 3 are variants, and the dispatcher plan for these variants is the plan 1. So we have two variants, query ID 2 and query ID 3, and the dispatcher is the plan 1. So let's look at the variant queries. So I will use the query store query text, query store query, join with query variant looking for the query ID. So I'll look for the variant queries. And the variant queries appear, as we saw before, it's the query itself, the select itself, including the query hint included on the PSP queries. Now let's look on the dispatcher query. I will join again the sysquery store query, sysquery store query text, and check the dispatcher ID, the parent query ID. And here we find, in this case, we find the select. In query store, what is stored is the select without any hint. This is the dispatcher plan. I can look to the plan itself of the dispatcher plan, also using query store. Open the plan, and you'll see the same multiple plans. So now SQL Server is capable to hold multiple query plans for the same query according the number of rows that query will return. And this is a great solution for the parameter sniffing problem that we have been talking about during the entire session. Now let's talk about cardinality estimator feedback, CE feedback. What's that? We're talking about the cardinality estimator. What is the cardinality estimator? The cardinality estimator is the query processing component responsible to estimate the number of rows which will be returned by a query. So the responsibility of this component is to estimate the return of a query. It's not about the CE, about the cardinality estimator itself. It's about the CE techniques. Why I'm talking this? Because many SQL Server versions ago, if I'm not mistaken, it was 2014 or 2012, the cardinality estimator got a new version. It got many new features. It was the first time in years that the cardinality estimator got new features. And at that time, we had the option to choose, would we like to use the new cardinality estimator or would we like to use the old cardinality estimator? But this is about 10 years ago. Who was there, who has good memory will remind that. But what's important is that the first time that I saw this, because I was there, I lived at that time, the first time I saw CE feedback, the first thing that came to my mind was that time. Is it about choosing which CE to use, which cardinality estimator version to use? No, it's not about which cardinality estimator version to use. It's about each technique used by the cardinality estimator. The cardinality estimator has many techniques to estimate the number of returned rows. And on each of these techniques, the cardinality estimator takes a decision, makes an important decision for us. We'll go this way and will not go this way. It's a decision made by the C. And now the cardinality estimator feedback can reveal the results of this decision about the decision applied on each C technique and create a feedback. Specify, no, let's go in a different way. So the cardinality estimator can see the result of the decision taken and decide to go in a different way. That's what the C feedback is about. At the moment, there is a feedback for 3 different C techniques. Feedback for 3 different C techniques are implemented. These techniques are the predicate independence versus correlation of the predicate, joint containment assumptions, a choice between simple or base, or row goal. Each one of these could take a lot of time to talk about. I will try to summarize a bit of these decisions that the cardinality estimator takes. So, predicate independence. Let's see this example. State province ID equal 79 and city equal Redmond. So there are 2 predicates in this query. And the cardinality estimator needs to decide if it will consider these 2 predicates related to each other, or if it will consider that they are independent. So, is there a relation between the predicate fields? That's the point. In complete independence, partial correlation or full correlation, these are the options. And the full behavior is a complete independence. But look to this query. We are seeing on this query that these fields are related. The city is inside the province. These fields are related, so the estimation could be better if there were a correlation. This is an example about correlation and independence. About joint containment, simple containment, about the correlation between joint predicates. Trying to summarize what this means. This means, will the processing be first of the filters and then process the joins? Or no correlation between join and predicates? Join and predicates are correlated, or there is no correlation? First, we will estimate joins and then estimate filters. What goes first? The filters go first or the join go first? This is called joint containment. And row goal. Look to this example. This example is using a top 1. Row goal is exactly for these situations. This example is using a top 1. Using row goal, sometimes the cardinality estimator can lead to a decision to make an index scan. Oh, it's only to get 1 row. If we make a simple scan of some pages on the index or something, we will find this row easier than if we make a seek. So Go can use this decision when applying a top. So apply to queries using top, scanning a few pages enough, or a seek is needed. That's the decision that the Go needs to make. And the Go is the full. It means that it will try to scan a few pages to return the top instead of using a seek. And the feedback, Go or the other C feedbacks, they can be disabled. Let's see an example of this. Let's see a demonstration of the C feedback. So C feedback. Now I'm using a different database. I'm using the AdventureWorks 2016. You can see here AdventureWorks 2016 extension. And I will create a session to see the cardinality estimate of feedback, an extended event session. We will see the feedback happening on this extended event session. See feedback, which is not started. Let's start the session. So we can see the C feedback session is now started. Let's take a look on watch live data. Now let's use the database. AdventureWorks 2016. Clear query store data and the procedure cache. And I will execute this query. This is the exactly query in this slide, on this slide. 15 times. I will execute this query 15 times. So let's see the feedback. Nothing happened. But now I will execute the same query one more time. One more time I will execute this query. So it immediately started the analysis of the C feedback. What I just illustrated, there is a magic number for the C feedback? Well, in some ways we are seeing a magic number for the C feedback, 15 plus 1, but is a non-documented number, and Microsoft doesn't recommend anyone to rely on this. Microsoft doesn't recommend anyone to rely on this number. So, at the moment, this is being analyzed, the feedback is being analyzed. If I take a look on the C feedback, I can see there is a record of a C feedback, but it's pending validation. The C feedback is pending validation. And the C feedback uses query store hints to execute. But if I check the query store hints, I have no hint implemented. But now I will execute the same query one more time. One more time the same query, and we have the validation. The validation event happened. Let's see the result of the validation, the C query store plan feedback. As you can note on this result in the C query store plan feedback, the verification passed. This means that the CE feedback is approved. So the CE feedback is active. And how can we see this feedback is active? The CE feedback use query store hints to be implemented. So in this case, we have a query store hint applied to our query. So we have the query store hint assume mean selectivity for filter estimate. As you may notice for this result, the verification passed. This means that the C feedback is approved. So the feedback is active. We can see this from the C query store plan feedback. But another way to check this is on the query store query hints. Cardinality estimator feedbacks are implemented as query store query hints. And this illustrates what I was talking about in the beginning. The features relate to each other. The features depend on each other. We need to understand one to understand the others. So the cardinality estimator feedback uses query store query hint and applies the hint assume mean selectivity for filter estimates to define a correlation between the query predicate. And in this case, this query now will be executed using a correlation between the query predicates. So this example is the example of one of the features that the CE feedback can analyze. The CE feedback at the moment can analyze 3 different features on our queries related to the cardinality estimator. This is an example of one of them, which is the predicate correlation or independence. Let's get back to our slides and let's talk a bit about the important shift of some concepts. According to technology evolves, some concepts change in importance, and some details that become our daily routine may change. We may need to change our mindset. Let's see some examples. Query plan cache. What happens when we clear the cache? Let's compare the before and after. Before, the queries are recompiled. We clear the cache, the queries are recompiled. I even saw some blogs, some articles mentioning that depending on the environment, this may not be a so big deal, may not be a so huge impact. The queries will only be recompiled. Usual recompilation time, nothing more. Okay, and after all these new features that we are talking about, what will happen? DOP feedbacks will be revalidated. So every query with a DOP feedback will pass by a revalidation process. PSPs will be completely regenerated, will be dropped if we clear the cache, and regenerated. Although they are stored in query store as well, they are stored as a historical purpose in query store. PSP doesn't depend on query store, it uses the plain cache. If we clear the cache, we lose the PSPs. And this is an example about the cache. And in relation about query store, what happened before and after? Before, if we cleared the query store in the past, we lose the history of our query. Okay. We may have a lack of plan regression recognition. We can recognize that a plan regression happened. But maybe this is okay for many people in many situations. But what happens now if we clear the query store? We lose the doc feedbacks. We lose the memory grant feedback. We lose query store hints, which means that will lose C feedbacks as well. So, the point that I'm highlighting is how a mindset change may be needed in relation to query store and query plan cache, in relation to the importance about clearing this. We were in a stage where query store was side 2 and the query plan cache. We always say to not clear it in production, but there was already some blog posts mentioning what the consequences, not so big. Now it is. Now it is. The consequence of this is bigger. So we need to stay aware about and make a mindset change in relation to the consequence of some daily routines. Some reference: a video achieving wonders with query store, a blog post about query store hints. It's mentioning only Azure SQL database because this blog post was when it was released on Azure SQL database, and the GitHub link for Boboat intelligence query process samples. Most of the demos I made during this session were from this GitHub. You find very useful content inside this GitHub. I recommend a lot. Thank you very much for attending this session. Let me leave you with my contact one more time. And it will be a pleasure to stay in touch. It will be a pleasure to connect and stay in touch. Thank you very much for attending this session.